Okay, so welcome back to this next video in which we are discussing Pavlovian or classical conditioning. Right, we are in the process of discussing the action potential so that we will be in a position to understand the mechanism underlying how the serotonin released by the L29 neuron onto the axon terminal of the L1 sensory neuron is going to lead to a long-term increase in the amount of neurotransmitter released by the axon terminal of that L1 neuron. Okay, right. We were in the process of discussing the voltage-gated potassium channels. So, these voltage-gated potassium channels were actually activated to open at the threshold potential, i.e. down at negative 40 millivolts when the voltage-gated sodium channels were activated to open. It's just they take much longer to open than the voltage-gated sodium channels. The voltage-gated sodium channels open extremely rapidly, whereas the voltage-gated potassium channels sort of clunk along and take much longer to open. Okay, so when they finally do get around to opening, it's about the time when the voltage-gated sodium channels are just calling it a day and closing. So the voltage-gated sodium channels close, and now these voltage-gated potassium channels open. So we now need to think about which direction is potassium going to move through these voltage-gated potassium channels in. Okay, so you've got a very high concentration of potassium in the cytoplasm. Okay, and you've got a much lower concentration of potassium in the extracellular fluid. Okay, so the concentration gradient favors the movement of potassium out of the cell. Meanwhile, we also have to consider the electrical gradient across the cell. Okay, so at the moment, the electrical potential difference across the cell membrane is at plus 40 millivolts. That means that the intracellular compartment's electrical potential is 40 millivolts higher than the extracellular compartment's electrical potential. Okay? So, potassium is a positively charged ion. It wants to be where the electrical potential is lower, which at the moment is the extracellular compartment. So not only is the concentration gradient saying move out, but also the electrical gradient at the moment is saying move out. Okay, so now you're going to get a movement of potassium out of the cell. Now what's the effect of this? Well, we are moving positively charged ions out of the cell. So we're taking positive charge away from the intracellular compartment and dumping it into the extracellular compartment. When you put a positive charge into the extracellular compartment, that will result in the electrical potential of the extracellular compartment going up. Meanwhile, you're removing positive charge from the intracellular compartment. That will result in the electrical potential of the intracellular compartment going down. So if we now want to know what is this going to do to the electrical potential difference across the cell, i.e. the electrical potential difference from extracellular to intracellular, well, let's look at this equation. This number here is now going down. This number here is going up. So that means this number is going to become more negative. So basically, you're going to get the repolarization of the electrical potential difference across the cell membrane. Okay, so what's going to happen is the electrical potential difference is going to go back down, basically, like so. Okay, now, you might think, wait a second, as soon as we get to a negative level, that will mean that the intracellular electrical potential is now lower than the electrical potential extracellularly. Okay, so won't the potassium ions want to now be on the intracellular side rather than the extracellular side? So won't this current stop? Well, the answer is you're correct. The potassium ions electrical gradient will now favour the movement of potassium into the cell rather than out of the cell. But basically the concentration gradient, which is around 40-fold, is still saying move out. Okay, so the concentration gradient says move out. The electrical gradient says move in. The question now is, who wins? Well, basically, the electrical potential difference across the cell membrane at the sort of level that we've got it here, which it looks to me around negative 15 millivolts, okay? That's not strong enough to stop the movement of potassium out, okay? So the concentration gradient will win. to get the electrical gradient strong enough that it completely stops the movement of potassium ions out, you need to take the electrical potential difference across the cell membrane to around negative 85 millivolts, which means you need to make the intracellular electrical compartment lower in electrical potential than the extracellular electric compartment by 85 millivolts, okay? And only then will the electrical gradient equal, i.e. it will be matched to the concentration gradient, and then you'll get no movement of potassium across the cell membrane. If, however, the electrical potential difference is less negative than this, okay, so maybe negative 75, which seems pretty strong, but not as strong as negative 85, then even at this sort of concentration, even at this electrical gradient, the concentration gradient will still win, okay, and you'll still get a net movement of potassium out. It'll be very small because the electrical gradient is fighting it so much, but you still do get a net movement out. And obviously if you go hyperpolarized of negative 85, so if you go to negative 95, then it will spin the opposite direction. So the electrical gradient will now be stronger than the concentration gradient, and you'll actually get the movement of potassium ions into the cell. Now, we're not going anywhere near negative 85 millivolts, so we do not need to worry about the potassium ions stopping moving out, basically. Whilst this channel is open, potassium will be moving out. Okay, and that will mean that the cell's electrical potential difference will repolarize, repolarize, and repolarize. Now, it will take the electrical potential difference across the cell membrane to slightly lower than negative 65 millivolts. Okay, so it gets slightly hyperpolarized of negative 65 millivolts, and then the voltage-gated potassium channels close, and it's just like the voltage-gated sodium channels where they stay open for a certain amount of time and then they close. So it's not the voltage that causes them to close, they just close anyway. Okay, and now we're back to just the normal leaky sodium and potassium channels being open. Okay, so what will happen is that resting membrane potential will return, the equilibrium will be reset up, and you'll go back to resting membrane potential. We haven't shown on this picture the leaky sodium and potassium channels. Okay, we're only showing the voltage-gated ones because those are the ones involved in the action potential. Okay, so that's now the action potential. Okay, now let's just discuss how the action potential then conducts along the cell membrane. So let's say we have a portion of membrane here in orange, which is undergoing an action potential. Okay, how does that cause an action potential to occur in the neighbouring portion of membrane, which I'll show in pink here? Okay, well basically when the orange portion of membrane undergoes an action potential, that's going to result in the depolarization of the electrical potential difference across that orange piece of cell membrane, which means that at some point you'll go up this spike. And what causes you to go up this spike? Well, it's sodium ions coming into the cell, so you're bringing a few sodium ions into the cell through these voltage-gated sodium channels mainly. Okay, now these sodium ions will diffuse away from this portion of membrane, basically. They'll diffuse off into the other neighbouring portions of cytoplasm, which means that they will diffuse into the cytoplasm underneath this pink piece of membrane. And what happens to the electrical potential of the intracellular compartment near this pink piece of membrane now? Well, if you're bringing sodium ions in over here, then what will happen is you will raise the electrical potential of that intracellular compartment over here. In addition, you have to think about the extracellular electrical potential as well. Okay, the extracellular electrical potential will not be changing that much. Okay, so now if we think about what the electrical potential difference across this cell membrane will do, well, we're raising the intracellular electrical potential. We're not really varying the extracellular electrical potential. So when we ask what the electrical potential difference across this pink portion of membrane over here is going to do, it means that it's going to become depolarized, because remember, the electrical potential difference from extracellular to intracellular is the electrical potential intracellularly minus the electrical potential extracellularly. If we're raising this number and leaving this number the same, the number is going to become less negative. So you're going to get the initial depolarization of the electrical potential difference of this pink portion of membrane. that will take the electrical potential difference of this portion, this pink portion of membrane, into this first portion of the action potential, the depolarizing interval, basically. Okay, and this pink portion of membrane, if it reaches the threshold potential, i.e. if the sodium ions diffusing in from this orange piece of membrane, which is undergoing an action potential, are sufficient to raise the electrical potential difference across this pink portion of membrane to negative 40 millivolts, then of course the voltage-gated sodium channels in this pink piece of membrane will activate and the action potential will fire. Okay, and then an action potential occurring in this pink portion of membrane will then cause an action potential in this blue piece of membrane, and an action potential occurring in this blue piece of membrane will cause an action potential in this green piece of membrane, and an action potential occurring in this green piece of membrane will cause an action potential in this turquoise piece of membrane. And that mechanism of conduction, where something happening here causes the same thing to happen here, causes the same thing to happen here, causes the same thing to happen here, is an example of saltatory conduction. Saltatory conduction doesn't just refer to action potentials propagating along nerves. Saltatory conduction is really the idea that you can conduct something by a disturbance here. Okay, so a disturbance, let's say here, causing a disturbance in its neighbour, which causes a disturbance in its neighbour, which causes a disturbance in its neighbour, which causes a disturbance in its neighbour. That's the idea of saltatory conduction, that something occurring at one point causes the same thing to occur at its neighbours, which then cause the same thing to occur at its neighbours. That's the idea of saltatory conduction. Okay, so it applies to action potentials propagating along cell membranes, but it's not exclusively applicable to action potentials conducting along cell membranes. Okay, now let's discuss how we get neurotransmitter released from axon terminals, and I promise you this discussion of action potentials is worthwhile if we really want to understand how we're going to get an increase in neurotransmitter release as a result of this serotonin. Right, so basically if we have our axon terminal here, okay, let's talk about how neurotransmitter is released. So what's going to happen is the action potential is going to propagate in, so it starts at this orange piece of membrane, it'll then propagate along, so the action potential is propagating along into the axon terminal, and eventually it will reach the presynaptic membrane here. So let's say it reaches this blue piece of membrane. Now, docked at the presynaptic membrane, you have what are known as synaptic vesicles. Okay, so these are vesicles which are full of neurotransmitter. So this is a synaptic vesicle. So let me put some green dots within these vesicles to represent the neurotransmitter. So these vesicles are full of neurotransmitter, and basically these synaptic vesicles, as they're called, which are just these vesicles full of neurotransmitter, they're going to fuse with the presynaptic membrane when an action potential arrives here, and that's how you're going to release neurotransmitter. Now the question is, how does the action potential trigger the fusion of these synaptic vesicles with the presynaptic membrane? Well, the answer is that within the membrane you have a special voltage-gated channel, okay? And this is a voltage-gated calcium channel. And the basic principle of what we're going to do is that we are going to turn the action potential, which is this electrical maneuver that's occurring at the cell membrane, we're going to turn it into something a little bit more physical, basically. We're going to turn it into a rise in the concentration of calcium within the cytoplasm of this axon terminal. Okay, now how can we couple electrical potential difference disturbances in the membrane to calcium going up within the cytoplasm? Well, we can have voltage-gated calcium channels. So, basically, when the blue portion of the membrane undergoes an action potential, it will become, well, the electrical potential difference across that blue piece of membrane will be depolarized. This will then activate these voltage-gated calcium channels in the blue portion of the membrane to open, and they will allow calcium to move into the cell. Now, we don't need to worry about the electrical potential difference across the membrane and think about the direction in which calcium is going to move. Whenever you open a voltage-gated calcium channel, or in fact any calcium channel, calcium always moves into the cell. And let me give you the reason why. The concentration of calcium in the extracellular fluid is usually around 1.5 millimolar. The concentration of calcium within the cytoplasm is around 100 nanomolar. Okay, that is a 15,000-fold gradient. That dwarfs the concentration gradients of sodium and potassium. Okay, there is no question which direction calcium is going to move when you open a voltage-gated calcium channel within the cell membrane. You get calcium coming in. Okay, and this calcium then triggers the exocytosis of these synaptic vesicles. The more calcium you let in, the more exocytosis you get. And what we are going to see is that the way serotonin activates an increase in the release of neurotransmitter is by leading to more calcium coming into the axon terminal, and therefore you release more of these synaptic vesicles which are docked at the presynaptic membrane. So an important thing to understand is that not every synaptic vesicle is going to be is going to be released when an action potential arrives. Okay, it will depend on how much calcium comes in. So if we increase the amount of calcium that comes in, you're going to get more synaptic vesicles being released, and therefore more neurotransmitter being released. Okay, right, so we now want to see how serotonin acting on this axon terminal of this L1 sensory neuron is going to lead to an increase in the amount of calcium that comes through these voltage-gated calcium channels into the axon terminal, and thereby an increase in the number of synaptic vesicles which we're going to release. Okay, right, so we'll call it there for this video, and we'll continue this discussion in the next video.